there are some far-reaching consequences of the mean value theorem that we will lean on very heavily in the coming chapter. The first of which will not blow your mind, and that's that if the derivative of a function is 0 at each point on the interval, then that function must be a constant. That's not surprising to you because we talked about derivatives and we actually introduced this idea that the derivative is the slope of the tangent line. If you have some curve or some function that is a constant value, it's always 4, always 2/3, then the slope of the tangent line, and in fact all tangent lines, will have a slope of 0 because that thing itself has a slope of 0. So graphically makes sense. We just went the other way. We said if a function is constant, its derivative is 0. We can use the mean value theorem to prove it the other direction. If the derivative is 0, then the function is constant. So let me just outline that for you quite quickly. The mean value theorem said that the average rate of change, so any 2 points, let's call them x1 and x2, the average rate of change would be f of x2 minus x1 over x2 minus x1. Now, if that first derivative is 0, by the mean value theorem, right? Because the mean value theorem said that this average rate of change had to equal the first derivative at some point c. However, if that first derivative is 0 and 0 all the time, then we see that the average rate of change, f of x2 minus f of x1 over x2 minus x1 is equal to 0. So that says that f of x2 is equal to f of x1 for all x. So we see no variation. F of x2 equals f of x1. That's a constant function for any value of x that we find. Now the second one that we use is a little more impressive, and that's that if the first derivative of one function equals the first derivative of another different function at each point, then there's some constant c that separates these two functions. They must be mostly the same and different only in constant to have the first derivative be the same. So such that f of x is the same thing as g of x plus some constant c. So consider these just for example. Let's say we have some function f of x equals 1/3 x cubed. Well, the derivative of 1/3 x cubed is x squared. If we have another function, g of x, whose derivative is x squared, he must look kind of like this function f of x, right? The only way to get a derivative of x squared is if I have the term 1/3 x cubed. That's the only way. You can't think of anything else that when you differentiate it, you get x squared. And in fact, there's nothing else that I have in my derivative here, so anything else that I've added, like some constant, let's say, 90, will then have a derivative of 0 and it disappears, right? So this first guy had a constant of 0, and this next guy had a constant of 90. The derivatives of both of those guys were 0. They're non-existent. They did not show up, but they otherwise had the same derivative. So the only thing that can be different with the original functions is some constant. Well, we can make this conclusion then. So any functions that have the derivative x squared must be from the family of functions that look like 1/3, family of functions that look like 1/3 x cubed. Now that's plus some constant. Graphically, back in college algebra or wherever you were before you were in calculus, you have some curve here. There's 1/3 x cubed. This belongs to a family of functions if we add constants. Maybe we add 1, so we have the same shape, but now this curve goes through the y-axis at 1, or we can take away 2, and now same curve, but it goes through the y-axis at -2. Same picture, we just translate it up and down the coordinate plane with this shift of a constant value at the end of the function. Now that is very impressive and important for us when we want to answer questions like this. Find all possible functions with the given derivative. So this is really touching on what we'll be doing in the next chapter. If we have a function whose derivative is 2x, what function was it? Like, what did he come from? What did we differentiate to get to 2x? And the answer is x squared. And you can check mentally, the derivative of x squared is, in fact, 2x. However, we could have any member of these family of functions. Anything that looks like x squared plus some constant, maybe plus pi, minus 96, any constant, when we differentiate it will go to 0 and then not show up in the derivative. So we're not surprised to not see it, but we have to allow for its presence. Okay, so what if we have y prime is 2x minus 1? What function y created this derivative? Well, the antiderivative, or the thing that makes a derivative of 2x, is x squared. What thing gives me a derivative of 1? That answer is x. The derivative of x is 1. So this term 2x came from x squared, and this term 1 came from x. That means all the functions who have derivatives like 2x minus 1 will look like this, plus some constant. So let's bump it up a notch. Now we have 3 terms in C. Excuse me, watch my notation there too. I'm not talking about the derivative, but the original function, y. So what do we differentiate to get 3x squared? X cubed. In fact, the derivative of x cubed is 3x. 3 minus 1 is 2. You told me already the thing we differentiated to get 2x was x squared, and the thing we differentiated to get minus 1 was x. So now we have 3 terms. They map exactly to their derivatives. If you want to check, just take the derivative of y and find that it matches y prime, but allow for the fact that it's part of a family of functions, so we add C. Now these, of course, get a little bit more tough. We have a lot of derivatives that we've messed with, so not just algebraic power rules, what we saw before, but also trigonometric. So we might ask ourselves, which function has a derivative of secant squared? And that answer is tangent, because the derivative of tangent is secant squared, plus any constant c. So you could think of these derivatives as having this like secret plus 0 that generates a c. What about the square root of theta? You might think of this as theta to the 1/2. How do we get to theta to the 1/2? What thing did we differentiate to get a half? Well, to go backward from the power rule, I know when I did the differentiation I had to take away 1 from the power. So if my exponent was 3/2, when I take away 1, I will get 1/2. I also, though, would have a multiplier if I did the derivative here of 3/2, so I'd like to undo that because it's not present in the derivative. So it must be something of this form, 2/3 theta to the 3/2. And we could check with the derivative. If y is 2/3 theta to the 3/2, what is y prime? That would be 2/3 times, the derivative means bring the power down 3/2, theta to the 3/2, and then because we're differentiating, take away 1. So y prime cancels, right? 3's and the 2's are gone. I don't have any value out there, just theta to the 3/2 minus 1, and 3/2 minus 1, or 3 minus 2, is 1/2. So sure enough, if I choose this function, I will get that derivative, which is what was shown up here. So I'm good, except that I have to remember that there could be some constant. All right, then we just put them together for this next example. C, you told me the thing that has a derivative of the square root of theta is 2/3 theta to the 3/2, and the thing that differentiates to secant squared is tangent theta. There's a minus separating the two of them, and they're part of a family of functions.